guys. Today, our topic is autoencoders. What are autoencoders? We studied autoencoders as built of two things, the encoder part and the decoder part. The encoder takes the input and creates a latent representation or a hidden representation. So input vector goes in, a hidden representation vector comes out. In this picture, the letter H is used, and it's very common to use either the letter H or the letter Z for latent representation or hidden representation. That gets decoded and becomes the X prime vector, right? I used X tilde in my notation, right? So suppose you have only one hidden layer, then what happens? The activation function, the result of the activation is essentially, it's okay, hang on. Let me just first put it like this. Given an input, you create a hidden layer, isn't it? H. Now the dimensionality of the hidden layer, it need not be less than the dimensionality of the input layer. I've been continuously making a conical structure in which this is smaller than the dimensionality D of the hidden layer is smaller than the dimensionality of the input, right? This is a classic autoencoder, but then there are variants of the autoencoder that do what is called overrepresentation. Where D is actually bigger than N. You create a hidden representation that into a much higher dimensional space, but then you have a sparsity problem. You need to be able to manage the sparsity somehow. So those are slightly advanced topics. Since we are moving, we covered the encoders in just one session foundationally. So I keep to this simpler one, the lesser one. Suppose you don't have an activation function at all, and you have a simple hidden layer, like from input you go to H. So what happens? If you remove activations from your neurons, you say it's the identity activation function, it becomes W dot X plus bias term, right? In that case, it is just a principal component analysis. In fact, it is equivalent to a PCA. Right. So you can say, and we talked about it, it's a review. PCA is remember we said that it is a linear form of dimensionality reduction. And its generalization is an autoencoder, because what does the activation function do? It deforms the output, right? It deforms the affine transformations that things like a PCA would do. PCA would do a linear transformation, and activation function would go and deform that affine transform. And so that's one way to think about your autoencoders. And then the decoder is a mirror function, is the opposite of the encoder. It goes from the latent representation to an output representation. So if you look at the journey, the entire journey of the autoencoder, it's a journey of first applying F being the encoder function, G being the decoder function. So given an input, first you apply the F function, then you apply the G function. Is that simple, guys? At the end of it, your neural network is what? It's an approximator. It's a function. It's a differentiable continuous function on your input. So F is one function for the encoder. G applies on the output of F, which is H, and produces X prime. What is our loss? And so that is why it's called autoencoder. And people also call it self-supervised learning, or this debate has been there quite a while. Is it supervised learning? Is it unsupervised learning? And different people will have different interpretations. And in my view, those words supervised, unsupervised, are somewhat beginning to get uncomfortable in the modern world, where you have a whole continuum of algorithms, very clearly predictive algorithms, and unsupervised learning, pattern recognition algorithms. I would say that, roughly speaking, you can think of autoencoders as not supervised learning. Is it completely unsupervised learning? Well, sort of, except that there is a target variable, X prime, and you do a loss function between the input and the reconstructed input. That's why it's often called the self-supervised learning, right? Because you use the training data itself. Training data is the label. Remember, if this was yi in this equation, the output, the only difference is xi. If I replace with yi and I replace xi prime with yi hat, that would be your standard regression loss function, isn't it, guys? The only difference is the label is the input itself, right? And of course, this is your standard output, but it is conventional in the autoencoder world to call it not yi hat, but to call it xi prime. And so your loss function is the sum squared error, mean squared error. Actually, if it is a mean squared, I forgot to put a 1 over n, guys. Please add it. There is an error here. Again, it just shows I can be sloppy. This is, put a 1 over n in your notes here. How do I do that? Let me do that here itself and I'll upload it. Where is my observations? Lambda sum, okay. There we go. Hopefully it's better. Yeah, 1 over n. Yeah, so 1 over n, this is your mean squared error. So that is something to remember. Guys, take the quiz on autoencoders. Huh? It is important that you review your knowledge, do that. So there are a few things to know about the autoencoder. We will walk through it. Autoencoders have variety. If you look at how many kinds of autoencoders are there, I myself have looked at least 24, but I'm not the guru of autoencoders. I'm just a generalist deep learning person. I'm sure that there are gurus whose entire PhD thesis is on, new kinds of autoencoders. So they might come back and say, oh, only 24. We know 100 or something like that. So I don't know, but there are lovely websites devoted to only to autoencoders. So it is again a world in itself. Right? If you're in a hurry to write a research paper, this is a great topic. You can easily, easily is relative, with some amount of effort, but not extraordinary effort, you can think of new variations of autoencoders and write a paper. Right? Hint, those of you who want to do summer internship with me, this could be a very, very good topic. Pick a specific domain, problem domain, and for that problem domain, take one of the autoencoders. Let's think of variants of it, what changes you would make, what special things you would do, and you will get an autoencoder. You would get a new autoencoder, right? That works better for that particular problem set than anything else. So that is that. There are many variants to it. Now, one class of variants which is important is the variational autoencoder. I talked about it because they are generative models. I did not get time to cover variational autoencoders in the regular 3-hour session because we ran out of time. But what I would like to do is take one of the Sunday sessions, make it a longer session, and go into the variational autoencoder deeply, right? So remember that these Sunday sessions do happen. When they do happen, if at all, you can listen to the recording. If you miss it, that would be great. Some of the material, extra material, I cover there. Though for the course, if you know autoencoders, it's not that far of a stretch from there to variational autoencoders. Another thing that I would like to cover is the Wasserstein autoencoders, which is the state of the art. Remember that in the Monday lecture, I covered the Wasserstein GAN. But it just occurred to me that I did not cover the foundational concept of Wasserstein distance and Wasserstein autoencoders. I would love to cover all this. See, ultimately, what happens is it's very difficult to pack everything into a sort of an 8-week course. So you have to pick and choose as part of the curriculum design, not to make a course too heavy. And I think at this moment, we are at the limit of how much we can absorb in this limited amount of time. But anyway, some basic summary of the autoencoders. The autoencoders, the encoder and decoders are laterally symmetric opposites. Would you agree? If you look at it visually, they're just opposites. Another way to put is, whatever you're, roughly speaking, it is in some sense the inverse or the transpose of it. right? Is the transpose of the function in many ways, the weight function. Not really, because it's gone through all this sigmoids and the activation functions and that, but very rough, high level thinking, we can think of it like that. Um, in our basic autoencoder, we made it purely of fully connected layers because it's the only neural architecture at this moment. Fully connected layers, you connect. It turns out that that's not the only way to do it. One of the neural architectures you learn is convolutional neural networks. That is the last lecture. This is our 8th week. But what I have done is, because it exists, I have added it to the lab notebook, and so you can play with it. I'll just give you a 1-minute understanding of convolutional networks. Convolutional networks are amazing when it comes to image processing. It is the domain in which it is used most. It was inspired by the way cats, when people researched how does cat's eye and brain interact, what areas of the brain are lit up when a cat sees something, right? And different parts of the image of what the cat sees leads to the lighting or being processed in different areas of the brain. By studying that, the convolutional networks apparently were inspired. They're a great idea, convolutions. We will study that, though I must also say that for computer vision now, there is a big shift to visual transformers. Right. So visual transformers is next week, and I've put convolutional networks and if time permitting, recurrent neural networks, LSTMs, etc. to the last week, simply because I wanted to make sure that we cover transformers in depth before we go anywhere. They're far more important these days. So there are an odd number of layers. Why would there be an odd number of layers? Because in a pinch, if you see that whichever way you design your encoder and your decoder, there is this extra layer H. So if this has n number of nodes and this has n number of layers, sorry, n number of layers here, n number of layers here, then it will be 2n plus the hidden layer, 2n plus 1. 2n plus 1 is an odd number. Right? So you have an odd number of layers in the standard autoencoder. At this moment, we made it purely out of that. The activation functions for the internals is ReLU. Actually, if you look at the code, I have sort of played around, used TANH, ReLU. This is, by now, you are experts at activation function. This statement may or may not be true in the latest code because I keep playing around with it. You can check. So it would be either TANH or ReLU. But one of the fun things you can do is play with different activation functions. Try leaky ReLU, try CLU, try, I don't know, GILU, try TANH, etc. But sigmoid won't give you anything. It will just slow you down. TANH is the sigmoid, logistic function won't give you much, but in the sigmoid class, TANH would do you good. We are using the standard MSE loss function here. So in the exercises, we will use this as a loss function, right? And then this lab, we use the famous MNIST dataset. MNIST dataset, maybe a bit of history is important. The MNIST stands for Modified National Institute of Science and Technology. So National Institutes of, what is it? Standards. Okay, now I'm forgetting what NIST stands for. What is it? National Institute for Standards or Science and Technology? Yeah, we can quickly look up, guys, and tell me, enlighten me, I've forgotten. Unbelievable.
National Institute of Standards and Technology.
Standards and Technology, yes. And M stands for the so there was the data set that was produced by NIST, and then that data set was followed by, was modified or cleaned up a little bit. And so it is the modified NIST data set. It is a data set of handwriting, right? And handwriting is very, very important. Why is it important today? People, or at least it was customary that when people would send a postal mail, which some of you remember, you put something into an envelope and send it over. I mean, I'm sure all of you receive postal mails. in the US still, and the young people have all moved to email. So when you receive a postal mail, you have an envelope, and envelopes, when you get it commercially, then things are printed on it, address. But when you send a letter to your friend, which you may or may not have done in your lifetime, it was traditional that people would handwrite the address and put a stamp there and send it. Right? So a lot of mail in the US used to go with handwritten addresses on the envelope. Now, processing handwritten is very, very sort of laborious and for someone to understand what is the address. In the old time, a letter used to take a long time to be processed and reach its destination. Lots of people along the way had to reinterpret or understand what the address is. Today, it is an amazing thing that letters, the moment you put a letter into the mailbox, and assuming that you have handwritten it, believe it or not, there's no human being trying to figure out what address it is. It goes to a central location. There are AI machines, optical machines that look at that. They do handwriting recognition, and they figure out what address you're putting. And at the bottom of every envelope that you receive for a handwritten, you will see a little bit of a vertical lines there. That is a postal code, computer postal code of the address in computer language. And then the routers, automatically the sorters and routers along the way redirect your mail from place to place. And no human intervention happens after that till it reaches the postman who delivers mail on your street. The postman in the morning gets a box of mails belonging to your neighborhood. And then when the postman is coming by your particular house or your street, that's the only time another human being touches your envelope. So that efficiency has led to many, many good things. There is a concept of dead letters. Dead letters are letters that got completely lost or misunderstood or went to the wrong place. Right? Usually, if mails go to the wrong place, they are rerouted back to the right place and so forth. It used to be quite common for people to receive to lose emails or not emails, lose mails or postal mails and receive mails of some other people. Today, it practically doesn't happen. And so the concept, and also the concept of dead letter is more or less defunct. Very, very small proportion of letters actually get lost. Not only that, letters reach their destinations quite rapidly. It's surprising how quickly a letter posted from California, let's say, reaches New York. It is the basic transit time. Other than that, it is very fast. It wasn't like that a long time ago when it was a human-driven process. So there is a lot that is going on here in the history of deep neural networks. So people for the longest time have tried to create handwriting recognition systems, right? Classifiers that would tell whether this is a A or a B, or it's a 0 or a 9 or a 8 or something. MNIST is simpler. It is only about digits at this moment, the alphabet also, but we limit ourselves to digits, 0 to 9, and we recognize those digits, right? MNIST used to be the benchmark to test algorithms against. There was a time, Dennis, could you please make sure that the AC is down to 69? I'm feeling a bit warm here. You know how to turn it down? Yeah, thank you. So it used to be that we would, that algorithms would have accuracies in the 60s, 70s, or something like that. In fact, one of the big changes that came was support vector machines, which made a radical improvement in the accuracy of that. Today, the gold standard is deep neural networks. Right? In fact, the accuracy is so good with deep neural networks in recognizing digits. You did that in the digit classifier. I hope that was one of your labs. It is uncannily accurate, so that today we talk about the success rate in 99.98 or something like that %. And the few cases which are hard to, where there's a classification error, they are literally not possible to legitimately call those scribblings as any digit whatsoever. Right? We have an accuracy rate with machines that far exceeds that of human beings. Literally, they're beating human beings in handwriting recognition. One would have imagined handwriting recognition is a very, very human thing to do. Machines will never beat us at it. And yet, with deep neural networks, machines do far better. Right? Machines are getting far better than us for most things. As you can create specialized machines for each task, and it outdoes us. Where we outdo machines, of course, is in generalized intelligence. We are pretty good at many things, whereas a machine will be very good at one thing. Will learn to, a deep neural network model will learn to do one thing very well. So it's still a pursuit, perhaps, to be followed in the next 100 years to create generalized intelligence. So that's that. We'll be using the MNIST dataset in case the number of hidden layers can be. So what happens is I've created these classes for you, base autoencoder and so forth. So you have to, and I'll walk you through the code in a little bit. So you will see how to create it. It's not hard. You have the base autoencoder and you'll give it, I've made it open so that you can give it, you can sort of design your own autoencoder. Part of your homework is to design your autoencoder. Like decide in the first layer, I want so many elements. In the second, I want how many layers I have. And I've made it as simple as giving it an array of numbers. That's all. So there are certain classes that you'll find. We'll import those classes. I will just show you how it runs. So you train an autoencoder. So what does an autoencoder look like? Let's say that you create the most vanilla form of autoencoder, which I call the base autoencoder. Now the input dimension is 28 times 28. Why? 28 square. Why do you think I picked this unusual number 28? Could one of you guess it? Anyone?
I think Jin Lee and Manish might know.
Yeah. What was the size of the input data again?
Yes, MNIST images are 28 by 28 pixels.
Right. And that's pretty much the reason
Yes.
why we chose the input as the pixels, so that we can identify each one of these input dimensions by the 28 by 28 matrix.
That's right. And if you linearize it, then it becomes a single vector
Right.
whose size is 28 by 28, 28 times 28, 28.
Right.
And so that is what it is. If you look at the first layer, which takes in input features is 784, which is 28 square, and it produces an output of 64. So there is only one hidden layer, 64, and the second the sort of hidden layer then produces the latent vector. The latent dimensions I've kept is 16 dimensional. By the way, this is something for you to play with. What happens if you try to reduce it down to 2 dimensions? Ask yourself, are 2 dimensions enough to capture the information of a digit? Who knows? Play with it. 16 is what I took. Now, this is the kind of things you should play with. How many, what is the dimensionality of the latent space that you need to get a good autoencoder? Because that tells you how many dimensions you need to capture the richness of the input. Most of the information in the input. These are things that you should play with. So play with this. So 16, and what is the decoder is the opposite. It goes from 16 to 64 and from 64 to 784, which is so output feature dimension is the same as the input features dimension. Does this make sense, guys? Encoder, decoder, do they look sensible?
Right. And the output features for 16, that's always in the multiples of 16, right? Or
I just took, it's a convention that people tend to take powers of 2, right? For the layers. Now, for no rhyme or reason. Actually, recently there has been a very interesting interpretation coming from theoretical physics. What is the result? It shows that for neural networks, there is actually a good ratio between the number of layers and the number of nodes in each layer, right? That leads to pretty efficient, fully connected neural networks. I saw that paper recently. There's a book also now. There's a lovely book that has come out in Amazon. It's a very recent book. I will post it to you guys. But be prepared. You can understand it only if you understand quantum field theory and relativity. Okay? Because it literally uses arguments from those. I say it lovely book. Why? Because, well, I happen to be from those fields. But leaving that aside, there is a way to read mathematical books without reading the math. In the first pass, you just say, you read it, you say, they'll make some arguments and then say, and therefore we conclude that this works. So then you only need to read, therefore we conclude that this works. Right? And sort of glaze over everything in between. That's what I do. Whenever I take a math book, in the beginning, I just glaze through and pick up on some gems along the way. And then the second pass, I come and try to make more out of it and make more out of it. Typically, mathematical books are best read in multiple passes, or at least that's the way I do it. Okay? I'll point out to that, but anyway, this is a huge digression. The point is that it used to be everybody's favorite. How many layers, how many nodes in a layer they would do. People would tinker around, right? Most of deep learning is tinkering around. Guys, there is a very simple analogy. And the analogy is this. See, telescopes were discovered by the Dutch craftsmen. Or the magnifying glasses were already discovered. Arguably, the proto-telescopes were already there. And then Galileo put it all together into a telescope, and to look at the planets. But the optical theory was not well developed. Right? We did not have a full and clear understanding of why a telescope should be the way it is with its compound lenses and so forth. We had some understanding, but not all understanding. Some understanding was needed to make a good telescope, but there was a lot of tinkering around. Right? Much of science progresses in a very strange way. Quite often, tinkering around and experimentation produces some really good breakthroughs. And then the theoreticians follow and really understand why this works. They develop the subject, they put a theoretical foundation to the results. And so, on other occasions is the opposite. For example, black holes were predicted by Chandrasekhar. Right? What, in the 1920s, when he was traveling on a ship, they were only recently discovered and proven to exist experimentally. Gravitational waves were known to be there. Actually, when I was in graduate school doing my doctoral work in theoretical physics, it was well established that gravitational waves would be there. I remember that our research group was trying to build a gravitational wave detector. It took close to 30 years to successfully make a gravitational wave detector and actually detect gravitational waves. So sometimes theory is ahead of the experiments, and experiments catch up. When you look at deep learning, it is very evident that it is the world of tinkering. All the explanations that I've given you, they're true, but there is a lot that is not known. We just know the outlines of the theory. So don't ever have the illusion that we fully understand why deep neural networks work. Right? There's a bit of a magic around here, and it has a lot of people marvel and be frustrated. I remember there was a professor in computer vision who wrote an article. Actually, he said that, see, computer vision had such beautiful theories, like elegant theories of this and that and all sorts of models, and then came deep neural networks, right? Convolutionals and this and that, and it basically blew the state of the art based on those theories. And you looked at the deep neural network, and we'll do that in the next, in the 8th lecture, the convolutionals. And you look at it, and all it is a convolutional function, mathematically very simple. And if you understand deep neural networks, it's all just layers, layers, layers. So there'll be like so many filters and so on and so forth that you are sandwiching together. And lo and behold, it does an excellent job at computer vision tasks, a class of computer vision tasks. And it beats the state of the art of models based on actual computer vision theory. The fellow the professor wrote very interestingly with a reaction, which captures a feeling that people have with deep learning. They're both fascinated by the quality of the results, because for practical purposes, those results are amazing. They really move the state of the art forward. And yet they're disgusted with the lack of theory, because there's almost no theory in deep learning. What is it? It's just, some neurons firing, some activations, right? Some little bit of theory. I mean, there is some theory. I wouldn't say it's not there, but at this moment, the subject is by no means fully understood. So we are in the world of tinkering, guys. Huh? You can, in a very real sense, you can take whatever you have learned so far, just tinker with just create a little architecture with feed forwards and make some small changes, put some ideas and just tinker around. And there is a fairly good likelihood that you'll come to a breakthrough and come up with a particular variant of the neural architecture that does extremely well for some task. I know it from experience. People have been doing it in the labs. So, but if you ask this question, well, could we have derived this neural architecture from first principles? Is there a theory behind why this particular kind of a neural architecture works better than other kind? Or do we even know if this is the best kind of neural architecture? People will just shake their head and say, no, we are totally in the world of just tinkering around. So it is very much like building telescopes before optical theory came into optics. The physics of optics was really understood. Right? So that is a flavor of this world. And so get into the habit of tinkering. If you notice, almost all the homeworks that I give you in this, it is all about tinkering. Change the network, change the shape, do this, do that, small things. But develop a habit of tinkering and seeing how it affects the result. Because what you need to be an expert in this field is, the more you tinker, the more you get a gut sense, an intuitive sense that you can't explain why, but you will be able to find the optimal way of putting things together much more quickly than if you don't tinker around. Tinkerers develop a sense for it. Right? Now, there is a whole field called automated machine learning that tries to do it in using Bayesian learning, and I was going to tell you, but it is also not fully sufficient. There is a whole lot of tinkering that goes on still. Right, lot of the things are still tinkering around. So get into the habit of tinkering. Why did I take 64 as the hidden layer? I don't know. Why did I take 16 as the hidden dimension? That I know, because for MNIST has been so well studied. I know that if you take 2, it won't be enough. 4 won't be enough. By 8, it's getting better. 16, it really gets better. Okay. And try it out. Change the latency. Right now, when you download the lab, and today you will do the lab, change it to 2 and see what happens, right? Or 4 or 8 and see what happens. Now I ran it for 5 epochs. Why? The epochs run a bit slowly. Huh? It takes some time. So run it for 5 epochs. You look at the loss function. I'm plotting the loss function. By the way, I've simplified the code to an extent that I hope these elements are very easy to read. When you say autoencoder.train epochs is equal to 5, what am I trying to do, guys, here? Yeah, training the network for 5 epochs, right? Then I'm plotting the loss function, again, iterations. If I just train for 5 epochs, how come I have 9,000, close to 9,000 steps or iterations? What's the explanation for this? Could somebody give me an explanation for this?
You're saying why 9,000?
Yeah, why is it? Look at the x-axis. Why does it go all the way to 9,000?
Because it has not stabilized in terms of the loss and it continues to reduce.
Yes, but I just set epochs to 5. 5 and 9,000 are very different numbers. How did it go through so many iterations? Yeah, remember, guys, that epoch.
For each epoch, we run through the entire data set.
Exactly. So what do? We make mini batches of data. So one step is learning from one mini batch of data. That is one iteration. Because we have a lot of data, within an epoch, there are many, many iterations. Are we getting it, guys? That's why the x-axis goes to this. And as you can see, as Manish pointed out, yes, the loss does continually decrease. And you can see it here. The loss is decreasing slowly, I would say, relatively slowly. So now the question is, can you make the loss decrease below these numbers. That is a challenge. And last time you remember that you guys did a very good job of fitting the neural network to the curve, the hard curve for regression. So try here also, see if you can bring the loss lower. Now let's visualize the result. We gave it a 5. Now for each of them, this is the output. This is the X prime, and this is the X, the input. So when you look at the input and the output, would you say that if I gave it 5 and the 5 prime looks relatively like 5, 3 looks, there is some loss. Can you guys see the loss? When you compare the digits at the top and the digits corresponding digit in the second row, can you guys see that the output is not as sharp as the input? Would you agree, guys?
It seems slightly blurred.
Yeah, but the interesting thing is the input was 784 dimension. You reduced it to latent space of 16 dimensions. So what it means is 16 dimensions is enough to capture quite a bit of the information, isn't it? Right?
I have a
Yes.
question.
Yes, go ahead.
So I understand that the conceptual part behind autoencoders is it's taking something that's represented in a high dimension and representing the same thing in a lower dimension and then converting it back to the same dimension. But what is actually causing these individual neurons to activate and act in different ways in which as like it's different than any other kind of neural network, which is just fully connected?
No, it is a fully connected neural network in every sense. It is just a pinch. You just created a bottleneck in the middle. Right?
But you mentioned that there are also autoencoders where your D is greater than N. So how is that any different than?
Oh, okay. So why do we use that? The overrepresented or overcomplete neural net autoencoders. Why don't we keep it as a separate topic? Those are the sparse autoencoders.
Okay.
The thing. I'll come to those. I'll come to those. At this moment, put it in your back pocket that one day I'll answer that for you. Right?
Okay. But for now, I just need to know that this is going from, we can see 784, but 28 by 28 to now 16 by 16 almost.
Yeah. And so whatever the reconstruction is, it is reconstructed from just a 16-dimensional vector. 16-dimensional vector has been decoded back into a 784-dimensional image, and it looks pretty good. I wouldn't say very good, but it looks, well, a reasonable approximation to the input. Right? It means that the 16 dimension was able to capture a pretty good amount of information. So what you should do is go and play with different numbers, guys. 16. What happens if I make it 4? What happens if I make it 8? What happens if I make it 32? And what you will notice is that the encoders do well for certain digits and not so well for other digits. So for example, do you notice that zeros come through pretty well? Right? Wherever you see zeros come through reasonably well everywhere. The zeros look like zeros. They don't get destroyed, right? You will also notice that some other digits come through very well. 7 and 1 come through fairly well. 1 is particularly good. It comes through very well. Can you identify the digit?
You can see that 3 and 5 gets mixed up in, say, the first image, second row, I think 7th column.
Yeah, this one. This
5 and 3, yeah.
They're getting mixed up and things are not looking so nice. And which other, like 4 is a bit of a problem. Do you notice that this 4 here, the last row in the second set of images here, there's a 4 here, and look at the 4 here, is beginning to get a bit mangled, right?
And 8 and 3 are also getting mixed up.
Yes, 8 and 3 tendency to get mixed up. So, and this 8 here is looking almost, it's hard to tell whether it's a 9 or a 1 or a 8. Do you see where my mouse is? It's a little hard to tell that. So obviously, it is, first of all, it's impressive that it can do that. Secondly, we realize that, well, let's tinker around and do a better job. So which is your work, guys? First, reduce the latent space dimensionality and see the effect. How small can this dimensionality be? before the reconstructed image degrades unacceptably. So in other words, how much can you reduce before it becomes gibberish? Right. So for example, can you reduce it down to just one dimension and try to reconstruct it back from one dimension? Try it out. See if anything can be reconstructed from that. Do it to 2 dimensions. If you reduce it down to 2 dimensions, you'll have one lovely side benefit. 2 dimensions, you can plot it out. The hidden representation can be actually plotted out, isn't it? Now, what about if you add more hidden layers in between? Right? If you make the network richer, then maybe you can use less dimensions, but you can do much richer transformation, much better representation extraction, so that you get much better reconstruction. So play with that. How does the number of epochs have a difference? So I ran it for 1 epoch, no, 5 epochs. The notebook that Kyle has uploaded deliberately, it has been run with 1 epoch. All right. I invite you all to, in the break, download that notebook, play with it, and see how it looks how different it looks between 1 epoch and 5, or just do it on your own. Remember, 5 epochs will force you to take a coffee break. Huh? Or if your laptop is not powerful enough, it takes 3-4 minutes to run or 5 minutes to run. It takes almost a minute or more per epoch. Now, we learned about the denoising autoencoder. Does anybody remember what a denoising autoencoder was? Yeah. So you give it a noisy picture and you force it to clean that picture. Because if you could train an autoencoder in such a way that you take an original image, add a lot of noise to it, push it through the autoencoder, but the loss function you make not against the noisy image, but against the original image. The autoencoder will have to learn to filter out the noise, denoise it. Huh? And you can immediately see the value of it for cleaning up images, like grainy images. So the first autoencoder does a data compression, isn't it? Reduces it to lower dimension. But now the second denoising autoencoder removes noise. I ran it for 5 epochs. You can see that pretty soon it has stabilized. Maybe it was unnecessary to run for 5 epochs. Let's look at it. Yeah, the loss function. Yeah, loss function is still going down, but very slowly. Right? You can run it for more epochs and see what happens. Let's visualize the result. Oh, in this case, the results are not terribly, did I even run it? Epochs, train directory, yeah. So in this case, noise ratio, clearly I have not run it because I've not added enough noise. Let me add noise, then I'll run it again and it will take quite some time. And when you do, at this moment, notice that these images, noisy images, I did not add enough noise, but okay, even without adding.
I can share my screen to
Yeah.
show the noisy.
Yeah, why don't you share your screen? I'll walk you guys through it. And in the meanwhile, I'll make this thing run here on my machine. Yeah, we are looking at Kyle's screen. Yes. So, yeah, look at this. Could you please?
Yes, I can, yeah.
Yes. So you see 3 panels, guys, 3 rows. The first is the original image. The second is the same image, but we have added a lot of noise to it. I hope you can see the noise there, white, sparkly dust of white chalk on it. And the third is the output. The autoencoder has been trained to clean it out. And Kyle, I believe you have run it for only 1 epoch.
No, yes, I've run it for 1.
Yeah, so 1 is not enough. If you run, but let's do it in the break. Run it for 5 epochs. It will be far more impressive when you see the results for 5 epochs. Huh? But
Okay.
do it in the break. You fire it off in the break. But let me just explain it.
Sure.
So guys, when you look at this, you can clearly, would you see that if row 2 is the input after the autoencoder has been trained and you take it to the field to use, would you be impressed if row 2 was the input and row 3 was the output? Anybody sees the value of this kind of a thing? Right? It is getting there, by the way, that it has been trained on only 1 epoch. It's far more impressive when you see the neural network to be properly trained. And I hope we can do that. It's running on my machine, and after the break, we can show you. Right. So that calls for a break. Kyle will help you download all of this on your machine and set it up. I'll give you guys 20 minutes to set it up properly on your machine. Please help everyone, Kyle, to make sure everybody has this properly set up and they can run it.
Okay.
Walk
Sure.
them through the instructions.
Okay. So under the section hands-on labs and solutions, we have this lab 6 zip file. Click on it and it will automatically start downloading.
Is this updated with that added term for the MSE function? The 1/n?
No, it doesn't.
Okay.
So you can download it and store it somewhere where you can open with the Jupyter notebooks, right? So, and once you do that, so you should unzip your file and it should look something like this without these 2 zip files. It should look like this, where you have Autoencoder and SVLearn. Okay, so inside Autoencoder, inside the Autoencoder folder, you'll find this autoencoders.ipy notebook. Okay, so you'll have to run this notebook, and it has dependencies on SVLearn library. Okay, so do let me know if you face any troubles, and as usual you will have to change your in the notebook. There's one change you'll have to do which is you have to set the path, right? So currently it shows the path that I've set. Go ahead and change it to the path in your system. Okay.
Kyle, what do I do after I download it and unzip the file?
Open this Autoencoders notebook from Jupyter notebooks. Like open this notebook.
Autoencoders notebook. Okay.
Yeah. So it's inside the folder autoencoders.
Okay.
Is anyone having trouble downloading the lab file?
No.
Okay, thank you.
Yeah, it's still trying to download. So
After downloading, what do we do?
So unzip the folder.
Yeah, done.
And after unzipping it, open your Jupyter notebooks.
Yeah.
And
Then
you've opened it. Now go to the folder, Lab 6 folder. Okay, and click on Autoencoders folder. Go inside it and you'll find Autoencoders notebook. Run this notebook.
yeah, I opened that.
Okay. And without running the notebook, you should see these output images. Do you see them?
Yes, I see them.
Okay, good. So now you just start running from the top. And yeah, before running, this is the step you have to do. In sys.path.append, change this to your lab 6 folder.
Okay.
I don't have the IPyplot module installed.
You don't have it installed? Okay. Just install it.
Just pip install.
Yeah.
Okay.
Put an exclamation in the notebook itself.
Okay.
Install IPyplot.
Okay.
Is that the only thing I need to change? The path?
Yes.
Okay, got it. Thanks.
And you may want to do this as well. Pip install IPyplot.
Oh, okay.
Carl, we were going to put lab 6 in lab 1 folder, or where? I just keep it.
You can keep it anywhere where you have access from your Jupyter notebook homepage.
Hey, Kyle, what is that exclamation mark in front of P for?
That is for like using your command prompt.
Oh, so every time I issue a command prompt,
Yes.
I will need to put okay.
Yeah.
Thanks, that's something new for me. Thank you.
Kyle, were you able to run it for 5 epochs?
Yes, this is the output.
Yeah. So guys, if you compare the second and the third row, would you feel that it's a significant improvement as a denoising device? It is. It's not as great with the standard autoencoder. Are you using the convolutional one or the regular one? Variation of the, what about the regular one? Because we want, okay, so I'll probably show
Okay.
contrast my.
Shall I stop staring?
No, let me see whether mine even works.
Okay.
I didn't run it actually. So yeah, continue to share yours. Convolutional autoencoders. I am.
Can I share my screen to show you something really
Yes.
quick?
Definitely.
Sure.
Okay. So I'm in the denoising autoencoder section, and I'm
Yes.
seeing that these images are marked as noisy, but I don't see the same kind of noise on your it's not the same as your.
By default, I added only 30% of Gaussian noise, which is too little noise. You have
Okay.
to look pretty subtly to see the noise. What I would do is go up a little bit. I'll tell you how to add noise.
Mhm.
Go to the constructor. You go up a little more constructor. Yeah, more up. Yes. So here, no, yeah, stop that. Denoising. After the hidden layers, put a comma and just say noise underscore ratio is equal to 1. Try running this.
Okay.
This should hopefully produce some really good.
I'm training it with 5 epochs, so it takes maybe like a minute or two.
Yes, and then what's that?
Can you show that again?
Oh yeah. So could you, Manish, scroll up and show to everyone what change you made, so everyone can see that. Where you said ratio is equal to 5, scroll up a little bit more.
Oh, yeah.
So guys, this element in the denoising autoencoder, add one more parameter called noise ratio.
Stop moving.
Oh, go up again. Sorry. Yeah. So guys, I hope you all are trying this lab. Kyle, is everyone able to load this into the Jupyter notebook?
I think Jin, Amrit, and Dwani are able to. I
Okay.
think Manish is still. Manish, what is your status?
I am uploading the, I was getting some errors in the autoencoder file, so I'm kind of doing this again, trying to spot where the error is.
Okay.
So adding parameter.
Noise underscore ratio.
one,
Yeah.
That increase it from 30%.
0.3 to 1. Yeah, from 30% to 100. Yeah, see, the Gaussian is a very tiny signal in itself. And I was taking 1/3 of the signal. Yeah. Now
up to
scroll down.
100%.
Why is this not showing the noisy part? Something is amiss.
So I mean, I'm seeing that in the below images you have.
Yeah.
Then, but is this different?
No, something, yeah. Maybe, yeah, it's the same thing. This is a convolutional autoencoder. Some fishy, I'll have to see why the code is behaving strangely. Maybe there's a little bug, I might be repeating just the same first and second row as is without replacing noisy image. Hang on, scroll down, please.
Oh, sorry.
Original image, noisy image. I think there's a minor screw up. I'll see why it is, but it will work for the convolutionals.
Okay, and that extra parameter that you added to that function, what does it actually do? Why'd you set it equal to 1?
Yeah, it increases the amount of noise. See, what I do is to the image, I added a bit of Gaussian noise, right?
Uh-huh.
I didn't, so Gaussian noise is already tiny. I took 0.3 of it, which is too little noise. Then when you make it all the way to 1, you can even make it 2, then you add a lot more noise, but don't do it for the denoising autoencoder. I think there may be a slight bug in the code. Do it for denoising convolutional autoencoder.
Sure.
Because the convolutional, I know, is working quite well. I'll just see, or take it as a homework to figure out what the little tweak is. Go down, convolutional autoencoder. Below this is the denoising convolutional encoder. Yeah, so here you add the same noise ratio is equal to 1. Good. Now run this, or yeah. And set the number of epochs to 5. It will be more fun.
Oh, right.
Yeah, go stop
Can
it.
can I stop it from running, or?
I suppose you'll have to start at the top to include your, yeah, say 5. Now try to rerun it.
Okay, let me, okay.
Not in train, in the construct. Oh yeah, in train, epochs is in train. Yeah, you're right. Run it again, see what happens.
Kyle, is there something module that I need to install, IP plot?
Yeah,
Yes.
yeah. Just do a
Yeah. Amrit, can you show Manish the install?
whenever you see a library missing, just do a pip install.
Just this
So
line.
Manish, you see that line? Yeah.
Yeah.
Start with the exclamation. It will take you to the underlying shell. Yeah, so by now, guys, you must be realizing that it is a good idea to have a powerful machine. Because things are beginning to get slow on your laptops. I would like to take perhaps this weekend to go over variational autoencoders and possibly Wasserstein or distance. Maybe the next week I'll do Wasserstein distance. And the next week's lab will be on GANs, and we'll do transformers.
So, Asif, you also mentioned you wanted to cover W and B.
Oh, weights and biases and dashboards.
Mm.
Yes, that should be, oh goodness, there's so many topics, hard to squeeze in. We should do. So one of them would be the boards, the dashboards. That is a lab thing. So let's keep one Sunday for that.
And for regularization, I think skip connection and residual was also.
Skip connection and residuals, yes. So we need to have a theory session on skip connection and residuals. Okay.
Yeah.
Explaining what skip connections are and residuals are. By the way, guys, what's your general feedback on the textbook, this Inside Deep Learning? Are you guys liking it?
It's great.
It's a great textbook.
Yeah.
I can't understand it. I stopped after chapter 2.
Oh, Jen, if you're having that, set up time with me or with some, we'll help you walk through it. Like if the going gets tough, we can unblock you. And if you're in the Bay Area, remember, you can always come and meet me here at Support Vectors. You can schedule a time.
Oh, okay.
Where are you located?
San Francisco.
Oh, it's not that far. If you're willing to take the hike up to Fremont, we could sit.
Oh, I go to Fremont quite often.
Oh, you do? Yes.
Yeah. So, okay. What is the schedule on the weekend for you guys?
No, you'll have to schedule a time.
Oh, I had to schedule a time with you. Okay.
Yeah.
Okay, yeah, I can see it.
Yeah, you can see that compared to the noisy one, the cleanup is pretty good, isn't it?
Yeah, very minor. I can see this 9 over here has been kind of divergent to a 5 over here.
No, see, you have to remember, you never see the original panel. The purpose of a denoising is what you will get is the second row. Data will come as the second row. So you're
Mhm.
comparing the second row to the third row.
Yeah, but originally it was this, right?
Well,
Like,
the point is originally you don't know. No? It's like you have taken
oh, right, because you start off with inputting this itself.
exactly.
Okay.
So once the model is trained, you have a AI, basically you have a denoising filter now. Right. So
Mhm.
imagine that you took an iPhone picture in real candlelight, right, where things look very, very grainy. Now you take that grainy picture and you pass it through your autoencoder and it will come out clean.
Mm. Yeah, so I can see how this would be very beneficial for, as you were mentioning, like fill in the blanks. Autoencoders are very good for that.
That too. I should have
Mhm.
created an example for the masking one, fill in the blanks also. Yeah.
Okay, thank you. I can stop sharing my screen, I guess.
So guys, I'll show you the code now. I'll walk, which will be a straightforward walkthrough. But today is all about doing, guys. Huh? So the point is, we do things. Yeah. See, look at my screen, guys. Huh? Do you see the distinction between the very noisy ones and this one? And this is only at how many epochs? 5 epochs. Did I actually do 5 epochs? I don't know. We'll see. Now, there is this wonderful topic which I didn't run, variational autoencoders. Keep it in your back pocket. I'll explain it to you. And I haven't even taught you what is convolutional. What in the world is this convolutional neural net? So I'll give you, again, we are ahead of that because we're going to do convolutional in the 8th week. They are a different neural architecture, again, inspired by the cat's brain. The convolutional filters, lots of filters are applied, filters and pooling, right? Or filter layers are added, which are very different from the traditional feed-forward network, fully connected network. And just staying ahead of that, I put it here. Now, let me walk through the code. After that, guys, the rest of the lab, I want you folks, I know you are busy, you won't get time. I want you to stay here and finish the lab. In other words, do it. I'll just walk through the code so that it all looks easy. So output, like where to keep images, this makes sense. I created a class called base autoencoders. Right? It's a very simple autoencoder. You give it the input dimension, you give it the latent dimension. And if you want, optionally, you can give it, like when it says none, this is Python way of saying it is optional. So yeah, default. So you can give it hidden layers, no hidden layers, right? And this is a constructor, which by definition, of course, produces nothing. Now, there's some basic tests. You can't give input dimension less than 2. It doesn't make sense. Latent dimension, at this moment, it is like a lower dimensional representation. So we say that latent dimension cannot be smaller than input dimension, right? It cannot be negative, if not hidden. If there are no hidden layers, but if there are hidden layers, then do what? How do you determine the size of the hidden layers? You do this. If hidden layers are specified, do the hidden layers. That's all. There's a little bit of a magic here. Now, what do I do? You build all of these things. Now comes the forward pass, the encoder and the decoder. So let's go and build the encoder. You will see that the encoder building is dead simple. What do? You create an empty modules array. First, you append a linear layer made up of what? Input dimension, right? And hidden layers, some hidden layers, right? Then what do? You add, you also append some ReLU to all of this, right? If hidden layer, if there are hidden layers, then for each of the hidden layers, you do this business. You add a linear layer and a ReLU. So I'm using ReLU all over the place in the base one. right? Then module, append, that's it. Basically stacking them together. And now this thing has PyTorch has a simpler syntax and then sequential, which is what I'm using, star modules, right? Vector of modules. You're passing it. That is it. Build the decoder. If you look at the decoder, it's nothing but the hidden layers. You know, this is a Pythonic way of saying, just read it backwards, the hidden layers. Would you agree that it's pretty much the same thing written backwards? And so you have all of these modules. You start with the latent and you go back, keep on expanding. And finally, you expand it out to the input dimension. The output is the input dimension. So output layer, same size as the input layer. Oh, for some reason at the end, I put a tanh there. I am thinking why. Oh yeah, I wanted to produce results between -1 and 1 for some reason. No. Yeah, because images, the MNIST images, they are grayscaled. They have values from 0 to 256, and that has been scaled down to 0 to 1. So we will scale it back to 0 to 1. This function is a static function. It's shaped to image. You have a vector. You need to make it into a 28 by 28. How do you do that? Very simple. We take it, first of all, this tanh goes from -1 to 1. So if you take, you sort of, you add 1 to it, it will go from 0 to 2, and you divide it by half, it will go from 0 to 1, which is exactly what you want because the input was from 0 to 1. Just basic, manipulation of color scales, of the gray scales. Batch size, whatever the batch size was, channel was 1. We know that it's a monochromatic image. So by now you must be realizing that we are playing with images. So you have to have some very elementary familiarity with image manipulation, guys. This is not neural networks at all. It is just manipulating images in Python. I would suggest you become familiar with the vocabulary of images, right? So what does a channel mean? Channels are the RGB channel, red, blue, green channel, right? And the alpha channel, potentially the transparency channel. What does image size? How do you take an image, 2D image, a 3D image rather, with RGB values thrown in, and vectorize it or make it into a single vector, represent it as one long vector, right? And things like that. So this kind of syntax, guys, I would consider this as a homework and become familiar with it. And I put ample comments here to explain what I'm doing at each stage, right? The view is a PyTorch function that renders it into the shape that you want it. So you can take any vector and reshape it and say, it must have this many batch size, these many channels, image size, image size. That is the height and the width, right? This is the height and the width. You have to do that. And then original input also, when you get an image, what do you do with the image? You need to linearize it. In other words, flatten it out, 2-dimensional or 3-dimensional image into one line vector. Then you need to do some compression. Transformations, when you train the data, you need to do some transformations. First is that you need to convert it, a vector, into a tensor. Then you to normalize it. Normalize does what? It makes the, well, you all know what normalize it, but it will normalize it to a center of 0.5. Why? Because the grayscale values are from 0 to 1. So you want that the medium tone color should be 0.5. Right. So some of these things, there is a project, a library called Torch Vision. Again, we are jumping the gun, but when you do the deep learning, the computer vision class, we will go over this very, very carefully. All of these functions, the Torch Vision or the image manipulation is the first lecture or the first week in which you learn all these image manipulation techniques. But there you learn at great detail. Here, I've simplified the code to such an extent that if you try a little bit, you will understand it and use the book as a guide. You will immediately understand what we are doing, and look into the Torch Vision website also. It will give you documentation for this. Right? You load the data and then you run for the epoch for the data. You do this, you build input by flattening it. If you need to add noise, you will add noise. You create an output, you create a loss function, you optimizer. Everything after that should be a no-brainer. The only additional thing is after every 100 steps, we save some images. We save sample input output so that we can compare it. Remember in the Jupyter notebooks, we compare it. That is it. Huh? Plot loss is quite straightforward. You plot loss. Linearize that function. How does it do? You give it a tensor. What will it do? It will linearize it to a single vector. Right? Arbitrary long vector. That's all. Then the rest of it is straightforward. Now, convolutional neural network, you can sort of glance through it, but it won't make sense because we haven't done convolutions. We will do convolutions in the 8th week. Now, this is the 6th week. We'll do it in the 8th week. And there's nothing magical happening. We're just building, you notice that 2 simple convolutional layers rather than linear layers. That's all. The autoencoder structure remains the same. Now there's variational autoencoder. I think we should remove it from here because now it is in a separate class of its own, BAE. Here, variational autoencoders. I will teach the theory of it maybe this Sunday for those of you who are interested. Its main quality is that it is a generative autoencoder. You can, once you train it, you can create arbitrary many samples that look like the input data, that look like the data that you trained it on. So if you train it on shoes, now you can create all sorts of shoes, right? You trained it on people, now you can create all sorts of people and so on and so forth, right? So you can imagine that what we did with GAN is the next step. We will do this after some time, not now. So skip the variational part. So guys, what I would suggest is enough of theory. We have, it's already 8:42. I would like you to take the next hour completely to running the labs on your own. And also don't look at the variation, but look at the vanilla autoencoder. Try to understand this code, right? At least the base encoder you should understand properly. Base autoencoder, which is from line 34 to line it is a bit of code, but it should be very simple code, similar to what you're used to, 200. So it's about 150, 160 lines of code. I give it to you as a homework to study this code. The previous batches have found it fairly easy to understand after a while, but they have also said that it took them a couple of hours to study it properly. But run the Jupyter notebooks, guys, and do the labs. The homework that I mentioned in the class, treat it as a classwork, and please do it. Right, please do it. So this is it. Kyle, and could you please help people get through
Yes.
this? So guys,
Yeah.
post your, and everyone, post your updates. Show what happens. What happens if you run? So one of you try it out. What happens if you reduce the dimensionality to just 2? Right? Are you able to reconstruct anything? What you will notice is that it will be
That's pretty good. Does do a good job.
with 2, right?
Yeah.
Not all digits. It will do a good job for some digits and badly for others.
Okay.
Right?
Yeah,
So,
I'll check.
yeah, find out which digits it does a good job. For which digits it does not do a good job. Those are the things to play around with, guys. Right? Play with more layers, less layers. Play with more epochs, less epochs. But I hope the autoencoder looks simple, at least in utilizing the autoencoders. Are you all becoming a bit more familiar with it? In reality, what happens, guys, is that you don't write and practice autoencoders from scratch. There are libraries of autoencoders. People have published a lot of autoencoders. And you just take one and tinker with it a little bit. Play with the way you're going to play with my autoencoder, the one that we are releasing here at Support Vectors. In the same way, you're going to tinker around with other autoencoders that you find on the internet and use it for your real world problem to solve your company's whatever use case is there, domain problem that you're solving. Because it takes a bit of effort to design the autoencoders correctly and apply it to your problem domain. So learn to tinker with it. Today, your whole lab is to tinker with it. Huh? And at the end of it, autoencoders is this picture. It's as simple as that. It's one of the reason I started with autoencoders is because it's the simple neural architecture that is different from a random feed-forward network. It is a feed-forward network, but of a special kind. Any questions, guys, before we leave you guys to do the labs?